everyone. My name is Dr. Kelly Lepo, and I'm an education and outreach scientist at the Space Telescope Science Institute in Baltimore, Maryland. Today, I'd like to tell you about the science and engineering of the James Webb Space Telescope, which will launch in December 2021. We'll start off by talking about the history of Webb, then discuss why we want to look at the universe with infrared eyes, and then what infrared light even is. And we'll talk about the exciting science that Webb will enable. And finally, we'll discuss the telescope itself and the feats of engineering that went into creating Webb. The James Webb Space Telescope will solve mysteries in our own solar system, look beyond to distant worlds around other stars, and probe the mysterious structures and origins of our universe and our place in it. Why does it need to be in space, and why is it specializing in gathering infrared light? Let's briefly explore its history and goals. Earth's atmosphere filters out some of the light that reaches the Earth and blurs the light that does reach the ground. To capture more of the light in the universe, we must send telescopes to space that have specialized instruments. Starting in the 1990s, NASA launched a series of space-based observatories to study different wavelengths of light. The Spitzer Space Telescope, which operated from 2003 to 2020, the Hubble Space Telescope, which launched in 1990 and still operates today, and the Chandra X-ray Observatory, which launched in 1999 and also still operates today. What have they shown us? With each additional space telescope, we continue to learn an incredible amount about the universe. Telescopes observe different types of light, offering unique perspectives of objects in space. When observers around the world first reported seeing the Crab Nebula at top left in 1054 AD, they described it as a new star. Chandra gave us a new view into the heart of the nebula left behind by a supernova explosion, revealing new details about the area around the central pulsar. Chandra's observations and X-rays have allowed us to trace the movements of particles in a bright ring for more than 20 years. One object Spitzer studied is Zeta Ophiuchi, a bright star obscured by dust in most observations. Infrared light allowed us to see through the dust to learn that the star is sending out powerful winds that are making ripples in the dust, creating a bow shock like a boat does when it travels through the water. Hubble has revealed the finer details of the Ring Nebula, the gaseous layers cast off by a dying star. Thousands of comet-like filaments likely formed when hot stellar winds and radiation plowed into colder shells of gas and dust. Multiple telescopes showed us the antennae galaxies and all that's happening as two galaxies collide. In this image alone, we can trace the life cycle of massive stars from their formation in gas clouds to an afterlife as compact X-ray sources. Chandra data are in blue, Hubble data are in gold and brown, and Spitzer data are red. We've shown you a few of the objects that are closer to Earth, but what about those that are very far away? What do the earliest galaxies in the universe look like? One view stands out among the rest, the Hubble Deep Field, which was produced in 1995 and has led to a series of deep fields by Hubble and other observatories, including Chandra, in the decades since. On screen, we have the Hubble Ultra Deep Field, taken in 2014. This image contains approximately 10,000 galaxies that extend back in time to within a few 100 billion years of the Big Bang. In 1995, the first Hubble Deep Field was captured when researchers pointed the telescope at a single, nearly empty patch of sky for more than 10 days. This image combines data from many observations of that same patch of sky, equivalent to 25 days or 600 hours of observing time. When we look out into space, we are looking back in time. The light arriving at Earth from the farthest objects in the universe is light that left those objects billions of years ago. We see those objects not as they are today, but as they appeared long ago. We want to see even more of that light, to see the first galaxies. But that requires that we switch back to gathering infrared light and a new great observatory, the James Webb Space Telescope. As the most ambitious and complex astronomical space observatory ever, the James Webb Space Telescope will deliver amazing science, complementing the spectacular scientific discoveries made by other space science missions. Webb will match the incredible image quality offered by Hubble, but with infrared light instead of visible light. We'll go into depth about infrared light in a moment. Webb, Hubble, and many other observatories will work together. They'll target some of the same regions of the sky to provide simultaneous or follow-up observations in infrared light. Using infrared imaging at unparalleled sensitivity and resolution to detect faint infrared light, Webb's discoveries will revolutionize and enrich our understanding of the universe. To capture light that's traveled more than 13 billion years to reach us, from when the universe was only a few hundreds of millions of years old, we need a telescope that focuses on gathering light that has been stretched or redshifted over time into infrared light. Webb's sensitivity to infrared light allows us to see the ancient light of the first galaxies, which has been redshifted as it traveled towards Earth over billions of years. When Webb takes its first deep fields, we will see some of the first galaxies that formed in the universe. There's so much more that we will learn. Let's explore all of the amazing science that Webb will contribute. Scientists and engineers had a lot of information to build on when designing Webb, since other telescopes were designed and launched before it. Planning for Webb began in 1989. For context, Hubble was launched in 1990. New concepts and designs for Webb, like this one shown here, were developed in the 1990s. The Next Generation Space Telescope, as it was originally known, was renamed the James Webb Space Telescope in 2002. Construction also began on its instruments in 2002. New technologies were required. Along with a battery of tests at every stage of development, scientists and engineers took time to ensure each instrument operates as planned. As I mentioned earlier, Webb is also designed to capture infrared light. What is it? Let's look at it in detail. The rainbow of light that the human eye can see is a small portion of the total range of light, known in science as the electromagnetic spectrum. Telescopes can be engineered to detect light outside of the visible range to show us otherwise hidden regions of space. Webb detects near-infrared and mid-infrared wavelengths, the light beyond the red end of the visible spectrum. Let's look at this concept with more familiar objects. Visible light provides us with detailed information about our environment, including colors and textures, as seen with these meerkats and freshwater crocodile. In infrared light, we see different details. The meerkats glow dramatically. Their high metabolisms cause them to glow brightly in the infrared through insulating layers of fur. The freshwater crocodile is faintly brighter than the cool ground, which tells us it had recently been lounging in the pool of warm water you see in the lower left, which is the warmest thing in the picture. It's been out of the water long enough to start to cool down. Infrared is a type of light our eyes can't see. It's redder than red light. Everything is glowing, even if we can't see it with our eyes. Many things like computers and humans and animals all glow in infrared light. Let's go back to the electromagnetic spectrum and look at it in detail. The portion of the spectrum of light labeled visible with the colors of the rainbow is what humans detect as visible light. Beyond the red end of the visible spectrum, the wavelengths are longer than the human eye can detect. The portion of the spectrum immediately beyond red is called infrared. Longer wavelengths, including infrared light, are able to pass through areas of dense gas clouds and other matter in the universe. Shorter wavelengths get trapped, which means telescopes that specialize in visible light can't capture them. By detecting longer infrared wavelengths of light with Webb, we will be able to see cool stars and warm planets clearly for the first time. By specializing in infrared light, Webb will be able to see what's behind the dust that we see everywhere in the universe. The Eagle Nebula's pillars of creation were captured by the Hubble Space Telescope in visible light on the left and near-infrared light in the middle, and by the Spitzer Space Telescope in mid-infrared light on the right. Like Spitzer, Webb will be able to see through the dust in regions like this, but at high resolution like Hubble. What does each type of light show? In visible light, forming stars are inside dense cocoons of gas and dust, which block their visible light from reaching the telescope. Near-infrared light shines through all but the densest dust, revealing many stars in and around the pillars. Mid-infrared light shows the eroded pillars of gas and dust glow with heat from bright young stars. Webb's images help us see past the dust clouds and figure out what's going on in these dense regions in great detail for the first time. We now know why infrared light is so valuable. Let's look at what Webb will study. What was the universe like shortly after the Big Bang? What are the characteristics of galaxies as the universe aged over billions of years? What more will we learn about how stars form, live, and die? Since Webb can see through dust, what will it reveal about forming planets and other distant worlds? These are only a few of the questions Webb will help answer. Webb will contribute to all areas of astronomy, and its most exciting discoveries may be the ones that we didn't even anticipate. The science that will be done using the Webb telescope will bring us closer to NASA's overarching science goals of discovering the secrets of the universe and searching for life beyond Earth. Let's start with the early universe. Webb can peer deep into space, capturing some of the first galaxies that formed as the universe cooled down after the Big Bang over 13.5 billion years ago. During this period, known as the era of reionization, the universe was a very different place. The gas between galaxies was largely opaque to energetic light, shown on the left image, which makes it difficult to observe young galaxies. What allowed the universe to become completely ionized or transparent, eventually leading to the clear conditions detected in much of the universe today, which we see in the right image? When did it begin, and how long did this process take? Webb's infrared observations will help us create the first detailed snapshot of galaxies in the early universe and provide much more information than ever possible before. These new data will allow researchers to analyze individual objects to understand how the surrounding gas changed from neutral to ionized, creating the transparent universe that we see today. But how can Webb capture light from the early universe? As light travels through the expanding universe, light is stretched to longer wavelengths, which is called cosmological redshift. Light from stars that is emitted as ultraviolet light and visible light is stretched to the longer wavelengths of infrared light. This is the light that Webb will capture and how we can observe extremely distant galaxies. The galaxy shown in the insert, GN-Z11, was observed as it was 13.4 billion years in the past. That's just 400 million years after the Big Bang. Webb will show us even more galaxies that existed in the early universe. How will Webb do this? Researchers will examine individual galaxies in Webb's images and data. They will pinpoint how old each one is, leading to Webb's next science specialty, studying galaxies over time. By viewing the universe At different distances and eras, we have evidence that galaxies change over time. They grow, collide, and merge with each other. The most distant, earliest galaxies we have seen tend to be smaller and less structured than those in the nearby universe. However, the earliest galaxies in the universe are still undetected. This is because the universe is expanding, and as space itself stretches, so does the wavelengths of light from the first galaxies into infrared light. Webb will examine these early galaxies and eras that followed in new detail, providing essential insight and helping us learn more about how galaxies evolve. What's great about this is that Webb's observations will be added to Hubble's, so we'll learn more about dust, stars, and galaxies over cosmic time. Webb will also help us learn more about the history of the mergers and growth of galaxies, black holes, and the history of star formation. Webb will study black holes both near and far. In our own Milky Way, Webb will peer through obscuring dust to study the center of the galaxy, specifically our resident supermassive black hole Sagittarius A star and the stars that orbit it. In nearby galaxies, Webb will take high-resolution spectra or data to learn about the temperature, speeds, and compositions of the material at their centers. Researchers will use this data to measure the mass of the black holes at the center of the galaxies by mapping the speeds of the central gas and stars. Webb will also study the feedback loop between the central black hole, their powerful jets, and the formation of new stars in those galaxies. Quasars are another type of very distant but very bright, active, supermassive black hole. These are among the brightest objects in the distant universe. These supermassive black holes, typically located at the center of galaxies, are millions to billions of times the mass of the Sun. They feed on infalling matter and unleash fantastic torrents of radiation, outshining all of the stars in their host galaxy combined. Their jets and winds shape their host galaxy. Webb will study the properties of quasars and their galaxies and how the black holes influence the first stages of galaxy development in the very early universe. Webb could also address broader questions of how galaxies form, including the long-standing problem of which came first, the galaxy or the black hole. Next up for Webb, stars. These are two views of the same object. It's an area of star formation in the Carina Nebula nicknamed Mystic Mountain. Visible light shows how scorching radiation and fast winds from super hot new stars are shaping and compressing the pillar, causing new stars to form. But more forming stars remain unseen in its dusty, towering peaks. Near-infrared light reveals the stars behind the gaseous, dusty veil of the nebula. The foreground pillar becomes semi-transparent because infrared light from background stars penetrates through much of the dust. A few of the stars inside the pillar also become visible. Webb's view will show us even more details of star-forming regions. Its images and data will help us learn about the physical and chemical properties of stellar and planetary systems. It will also give us insight into their formation. Webb can also detect the molecules in star-forming regions, including the Small Magellanin Cloud shown here. While Webb will also capture spectacular images of space, its real power is in spectroscopy, which is a scientific method of studying objects and materials based on detailed patterns of brightness of their light spread out into its component colors. Astronomers will use spectra captured by Webb to study mature stars of different size, mass, age, color, temperature, evolutionary stage, and formation environment. Newly forming stars cocooned in dense clouds of gas and dust. Cold molecular clouds that collapse to form stars, gas and dust ejected from dying stars, and even the molecules between stars. Webb will explore planets in our own solar system and worlds that are light years away. It can gather data about Mars and Jupiter, which is shown in near-infrared light here, Saturn, Uranus, Neptune, and more distant Kuiper Belt objects to help us build a broader picture of objects in our own solar system. Webb will help us better understand Mars's atmosphere, map the cloud structures on Jupiter, Saturn, Uranus, and Neptune, study the seasonal weather and climate on the giant gas planets and their moons, and study the composition of asteroids and Kuiper Belt objects. But we know from other missions that there are many more planets out there. Webb will also study planets in our Milky Way galaxy, extending the scientific discoveries of other NASA missions. If you're interested in planets inside and outside our solar system, follow Webb closely. We're gonna learn a lot. Many observatories already study distant planets. What will Webb do differently? Warm planets glow brightly in infrared light, while their host stars usually don't shine as brightly at those wavelengths. Their innate contrast means infrared light is the ideal wavelength range to observe planets. From its position in space, and with its huge mirrors, Webb will be able to capture longer infrared wavelengths of light in high resolution for the first time. Webb's unique abilities to take very sharp and very fast images also allow it to spot smaller planets than other telescopes. The images shown here are direct observations of a distant solar system known as HR 8799. Most of the light of the star at the center is blocked by an instrument known as a coronagraph, making it possible to detect 4 planets. With multiple observations, it's clear that this is a solar system viewed from above. With its position in space, Webb can add to what we know about systems like this by providing considerably more detail with the same technique. This is a transmission spectrum of Earth's atmosphere. Before I get too far, I want to state that Webb will not observe Earth. This is an example to show the data, known as spectra, that Webb will produce when studying distant planets. This transmission spectrum shows wavelengths of sunlight that molecules like oxygen, water, carbon dioxide, and methane absorb. Measuring a planet's atmosphere from hundreds or thousands of light years away is not as daunting as it might sound, although it certainly requires specialized instruments and rigorous techniques. One method Webb will use is known as transmission spectroscopy. Webb will observe the star's spectrum and then the exoplanet as it passes in front of the star. Scientists will subtract the star's light from the spectrum to see which molecules in the planet's atmosphere absorbed light, which appears dips in the spectrum. Webb's data will also be transformed into models or maps of exoplanets to provide more information about exoplanets at each stage in their orbit. By using both imaging and spectroscopy, Webb will return incredible detail about planets we haven't been able to detect with other telescopes. Spectroscopy helps researchers identify the colors, temperatures, motion, and masses of celestial objects, helping us learn more about these distant worlds. Where will Webb orbit? Why does it have a hot and a cold side? Why is it an ambitious piece of engineering? Let's explore these questions and more, including what we will learn from Webb's images and data. Several innovative and powerful new technologies make Webb's ambitious science goals possible. Examples include specialized optics to align the mirrors, detectors that can capture and separate light from hundreds of sources at once, and thermal control systems. These technologies make Webb the most sophisticated and complex space science telescope ever created. Webb is a collection of movable parts that have been designed to fold into a compact formation that's considerably smaller than when the observatory is fully deployed. This allows it to just barely fit into a 5-meter or 16-foot rocket payload fairing. Since Webb's mirror needs to fold to fit, engineers ensured its 18 mirror segments can also be adjusted to form a single perfect focus. Each mirror segment has several actuators or tiny mechanical motors attached to the back, allowing operators to move each one separately. Webb's tennis court-sized sun shield is similarly deployed by 139 tiny mechanical motors called actuators, with an additional 8 motors and thousands of other components which unfold and stretch the 5 membranes of the sun shield to its final taut shape. Let's take a closer look at its mirrors. Webb has a 6.6 meter or 21.7 foot diameter primary mirror. It's quite large, and that's for several reasons. For context, Hubble's mirror is much smaller at 2.4 meters or 7.8 feet in diameter. Webb has to have a bigger mirror to capture high-resolution, Hubble-like details in infrared light. Its mirror also needs to be stable at very cold temperatures, 40 degrees Kelvin, roughly minus 390 degrees Fahrenheit or minus 235 degrees Celsius, which is why it's made out of beryllium, which is 6 times stronger than steel and 2/3 the density of aluminum. There are 18 hexagonal segments. They are hexagons so that the mirrors can be adjusted to align to form a circular shape. Each segment is coated in a very thin layer of gold, about 1,000 atoms thick. Gold was selected because it's the best reflector of infrared light. How will Webb conduct its science operations? Let's start with a bit of context. This is a section of the Virgo cluster of galaxies. This image is about 2/3 the size of the moon as you see it from Earth. Over top of that, we've placed Webb's 4 instruments. Each instrument is like a Swiss Army knife of more specialized components, with multiple ways of observing. Although some of the instruments are more suitable than others for observing specific types of targets, all 4 can be used for investigations of the wide variety of objects that make up the universe, including planets, stars, nebulas, and galaxies. Webb's 4 science instruments are sensitive to a range of infrared light. The near-infrared spectrograph, or NIRSpec, is one of Webb's versatile tools for near-infrared spectroscopy, which spreads light out into its component wavelengths like a rainbow. This instrument has the first multi-object spectrograph in space, known as a microshutter array. It can capture individual spectra of dozens of objects at once, making it ideal for efficiently studying many distant, faint galaxies. Next up is the Near-Infrared Imager and Slitless Spectrograph, or NIRIS. It will also gather spectra and photograph the universe at near-infrared wavelengths. It can study the composition of exoplanets' atmospheres, observe distant galaxies, and examine bright objects that are very close together. The Near-Infrared Camera, or NIRCam, is Webb's primary imager or camera. It delivers high-resolution imaging and spectroscopy for a wide variety of investigations. It will detect light from the earliest stars and galaxies in the process of formation, stars in nearby galaxies, young stars in the Milky Way, and objects from a distant region of our solar system called the Kuiper Belt. It can also track the motion of exoplanets as they orbit their star. The Mid-Infrared Instrument, or MIRI, is another powerhouse. It can take images and gather spectra, and it covers longer, redder, infrared wavelengths of light. As the only mid-infrared instrument, astronomers use MIRI to study cooler objects, like debris disks around stars, which emit most of their light in the mid-infrared, and extremely distant galaxies, whose light has been shifted to the mid-infrared over time. I've mentioned spectrographs and spectra several times. If you're not already familiar with them, it's probably because spectra typically appear as graphs, and they aren't quite as flashy as a telescope's images. But spectra are in fact humbly hanging out behind the scenes of some of the most intriguing headlines in astronomy, and they provide incredible amounts of information. Spectrographs are instruments that spread out light so that the brightness of individual wavelengths can be measured. The result is known as a spectrum. By looking at the resulting patterns and brightness, we can learn about the composition, surface temperature, density, and movement of objects in space like planets, stars, nebulas, and galaxies. Webb has different types of spectrographs, each designed for a slightly different purpose. Plus, Webb is the first telescope to have a multi-object spectrograph in space, which means we can get separate information from many objects, like individual stars or galaxies, with one observation. Webb orbits the Sun near the second Sun-Earth Lagrange point, often referred to as L2, a point where the gravity from the Sun and the Earth balance. The point is approximately 1.5 million kilometers or 930,000 miles from Earth on the far side of the Earth from the Sun. Webb can't orbit the Earth like Hubble because the visible light and infrared light from the Sun, Earth, and Moon would heat up the telescope's mirror and scientific instruments, causing the telescope itself to glow in infrared light, which would outshine the faint objects in space. Webb will not be located precisely at L2, but will move around in a halo orbit around L2 as it orbits the Sun. At L2, Webb can maintain a safe distance from the bright light of the Sun, Earth, and Moon while maintaining its position relative to Earth. The lower part of Webb, where its 5-layered sunshield is, faces the Sun. This is where its equipment that does not need to be cooled, like its solar panel, antennae, computer, gyroscopes, and navigational jets are. Its tennis court-sized sunshield protects Webb from external sources of light and heat, which ensures it can detect faint heat signals from very distant objects. It's very important for its observing side to be very, very cold. Webb science instruments are housed behind the mirror, separated from the warm communications and control technology by the sunshield. Webb needs both passive and active cooling. Its 5-layered sunshield provides passive cooling. The first layer of the sunshield is 2/1000th of an inch thick, while the other 4 layers are only about 1/1000th of an inch thick. In 2021, Webb was carefully folded up and loaded onto a ship, which passed through the Panama Canal on its way to French Guiana in South America, where it reached its launch site at the European spaceport located near Kourou. It's beneficial for launch sites to be located near the equator. The spin of the Earth can give additional push to the rocket. After launch and during the first month in space, on its way to the second Lagrange point, L2, Webb will undergo a complex unfolding sequence. Steps include deploying, tensioning, and separating Webb's sunshield, a 5-layer diamond-shaped structure the size of a tennis court, extending its secondary mirror support structure, and unfolding its primary mirror, which has a honeycomb pattern of 18 hexagonal gold-coated mirror segments. Deployment and commissioning will take time, at least 6 months. Engineers and scientists will carefully activate and confirm each and every instrument is working properly before the first, but still unfocused image of a starfield is delivered about 2 months after it launches. In the 4th month after launch, Webb will complete its first orbit around L2 and take the first focused image. This will show that the mirrors are aligned. After the 6th-month mark, Webb will begin its science mission and start to conduct routine science operations. Every great relationship is based on excellent communication, right? The Space Telescope Science Institute, STSCI in Baltimore, Maryland, plays a key role in communicating with Webb. It hosts Webb's Mission Operations Center, where engineers and scientists command and control the telescope. Commands from STSCI travel to the Deep Space Network, or DSN, which transmits them to Webb. Webb's data then returns through the Deep Space Network to STSCI, where the data Webb took are then processed, distributed to the scientific community, and archived. And one more thing before we go. I'd like to mention that Webb has been an international collaboration since the beginning. In addition to the United States, 14 countries are involved in building the Webb telescope: Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom. Additional member states in Europe also contribute to the European Space Agency, or ESA. NASA is the lead partner on the project, working in collaboration with ESA and the Canadian Space Agency, or CSA. The Space Telescope Science Institute, STSCI, conducts the science and mission operations from its Baltimore, Maryland headquarters. As the lead agency, NASA has overall responsibility for the Webb mission. More than 120 American, European, and Canadian universities, organizations, and companies in 14 countries and over 29 US states contribute to Webb. Who's ready for Webb's image, data, and discoveries to start rolling in? Webb will capture light from the first generation of galaxies in the early universe, help us map how galaxies change over time, study how stars form, live, and die, and explore distant worlds. About 6 months after it launches, Webb will begin its science mission and start to conduct routine science operations. And then the news releases will start making exciting announcements. Thank you so much for taking the time to watch this presentation and learning about Webb. And I hope you are all as excited as I am for the great science to come.